Hello everyone, my name is Zhang. I'm working with Dr. Myoungsoo Zhang at the Computer Architecture and the Memory System Lab at the University of Texas. Before we step into our work, I want to use one slide to summarize our work. Firstly, the state-of-art SSD integrated much more internal resources compared to traditional one. However, no one considered how the growing internal resources impact the power, energy, and some factors on SSD. So our goal is want to invoke the importance of power, energy, and temperature issues in high-end SSD. We want to address the critical issues related to the growing internal resources. To achieve our goal, we analyze the challenges of SSDs integrating more resources. We cover 4 aspects. Firstly, operating temperatures. Secondly, we want to talk about the dynamic power behaviors. The third is energy consumption. At last, we want to address the overheating and the power throttling issues. Motivation. These figures show the structure of state-of-art SSD. Nowadays, state-of-art SSD utilize PCIe as its host interface, but PCIe has huge bandwidth. It is about 32 gigabytes per second. As we know, a single flash chip only has 1.6 to 200 megabytes per second. It is too small compared to the PCIe interface. As for the channels, the maximum bandwidth is about 400 megabytes. It is still too far away from the PCIe interface. So to reach the bandwidth, the researchers may use many chips to utilize chip-level parallelism, and they use many channels to utilize channel-level parallelisms. Another challenge is the controllers. New features of modern SSD utilize complicated error correction and the huge DRAM size. This makes single computation unit cannot satisfy the requirements. So multiple controllers with many cores are utilized in modern SSDs. To sum up, there will be more and more resources are integrated in state-of-art SSD. These figures show the trend of key components in SSD. The red line shows that the number of chips has been increased 64 times since 2002. And the black line shows the number of channels has increased by 64 times since 2002. Following this trend, we believe there will be more and more internal resources in the future. These massive integrated power contributors will cause the potential power concerns. So we believe it is essential to study power, energy, and some factors in modern SSD. To build up our evaluation, we want to cover the various SSDs in the market. So we choose 3 SSD as our test bed. The first test bed is traditional SSD. These traditional SSD have limited resources, such as 3 cores, 8 channels, 64 chips, and 256 megabyte DRAM. The second SSD compared to the baseline SSD is multi-core SSD. Multi-core SSD has more cores and more DRAM size. The third SSD is multi-resource SSD. Compared to multi-core SSD, it has more chips and channels. For our workloads, we generate 4 random access and sequential access with data size from 4 kilobytes to 4 megabytes. We also cover that the SSD has different characteristics as the I/O service processed. So we separate the device into 2 status. One is pristine device. The second is aged device. Pristine device is SSD with default factory setting, and aged device we just mimic the aged SSD. So after all, we have 192 different configurations to simulate the real world. Next, we will talk about our findings in operating temperature. These figures show the temperatures with different input data size. The x-axis has 11 different input data size, and the y-axis is temperature. The pink, the line, the black line and the purple line in the slides is presents the SPSSD. SPSSD is the baseline SSD. So it has very good temperature behavior. Oh, sorry about it. Look at these slides. The temperature ranges from 95 to 120 degrees. Compared to, and also the SPSSD has little impact from the virus request size. The next line shows the multi-resource SSD. Multi-resource has huge higher temperature compared to the SPSSD. It has about 58%. Multi-resources, this makes multi-resources SSD not suitable for many workloads. Let's look at the green box in the figure. The temperature increased from 134 degrees to 173 degrees. So the increment is so drastical. The reason behind of this is because as the input data size getting bigger, so the internal resources such as channels and the chips will be more to working in together. In that case, so many power consuming components working together, the temperature will be increased. Look at the red box. The temperature saturated when the data size increases to a certain level. I will explain it later. We have other findings in dynamic power behavior. In dynamic power behaviors, the SPSSD also is a good low power device. It has a power from 2 watt to 4 watt. But a high performance SSD have 15 watt and 17 watt. After all, it has 3.5 times more power and 4.5 times more powers compared to SPSSD. Look at the red box. The power also increased with the data size increased. And the red box, the data size as the data size increases to a certain level, the power saturates. I will explain it later. Next, we will talk about our findings in energy consumption. In energy consumption, the common presumption is that high-performance SSD can save energy because there's higher bandwidth, lower latency, and the shortened execution time. However, let's look at these figures. These figures show the energy with different input data size. So you can easily find out SPSSD is much short. The energy of SPSSD is much lower than high-performance SSD. It's about 95% degrees. So we say high-performance SSD still costs more energy than SPSSD. So the reason behind all of this is high-performance SSD require more powers to feed its internal resources. Lastly, I want to talk about more of the overheating problems and the power throttling issues. As we know, the temperature increase to a certain level, the heat output will lead to more function of SSD. So we call it overheating problems. These figures show the time series analysis of temperature. We separate it into 4 graphs, depend on different data size. We can easily find out from the figure, as the temperature reaches 180 degrees, the device level protection mechanism dynamically reduces the heat output to prevent the SSD from overheating. Let's make the saturation point in the slides, and we call it overheating point. We can from the overheating point, the device with small input data size did not hit the overheating point. However, the device with larger data size hits the overheating point at a very early stage. The reason behind all of this is because the larger input data size will invoke more power-consuming components. These power-consuming components will increase the temperature. The most important thing we want to know is how the temperature can be controlled by the device-level protection mechanism. It can be explained in these slides. As the power is automatically decreased at the overheating point to control the heat output. This is automatically due by the device level mechanisms. Look at the overheating point. The decrement is about 16%, 15%, and 50%. This decreasement can help to protect the SSD from overheating, and another benefit is it can reduce the power. But is this good enough for our SSD? I don't think so, because look at the overheating point in the slides. The huge performance has decreased at the overheating point. They are 18%, 15%, and 10%, depends on different data size. The protection mechanisms slows the power by turning off the active resource. That's why the performance get decreased. So in conclusion, less power reduce the temperature, but however, they will limit the active resources. Well, from this phenomena, we make assumption: is it good enough? Is it practical to input memory resources into the SSD? We don't think so, because as the device reaches the overheating point, this device, the internal resources will be turned off by the protection mechanism. So after all, overheating problems and the power throttling will hinder SSD from integrating more resources. Conclusions. We have found out several critical findings. Firstly, high-performance SSD generate higher temperature, consume large power and energies than conventional SSD. It is not acceptable for many work conditions. Another findings, we found out overheating problems and the power throttling issues are holding back the state-of-art SSD from achieving potential performance gains. So in our future work, we want to study more about hardware and software optimization to improve the power and energy efficiency of SSDs. That's all. Thank you.
If those SSDs were made byte addressable and bypass the I/O stack and the PCI Express interface and all this other jazz, if you got rid of all that, would you still have these power problems with it, do you think?
Could you tell me what's the meaning of bypass through the SSD? I mean,
so in other words,
you make the SSD as a cache, or? Right.
So in other words, if you made it, just put it, you could somehow hang it in the memory bus.
Oh, I understand. So
get it out of PCI Express, get rid of the I/O chain and all that. Would you still have the same for big 4 megabyte block writes in byte addressable? Would you still have the same power problems?
Unfortunately, we do not test this kind of conditions.
I'm asking you to make a conjecture.
Okay. So in that case, we may think about the data request is not full. So at that time, the data request is, there's few data requests because of bypass. So in that case, the results may be affected. Maybe the temperature will be decreased because of your bypass.
Okay.
Pradeep Kumar from George Washington University. So it's a nice talk. So I have a additional question here. So there are many resources which are inside SSDs. Those are like DRAM or maybe SRAM and CPUs and many other things. So did you try to classify like adding which component generates more heat or requires more energy?
Excuse me, could you speak, could you represent again?
Yeah, I'll try again. So an SSD, like the resource-rich SSD has a lot of other stuff. For instance, SRAM, CPUs, and many other things, whatever you mentioned. So did you analyze like which component has, which component is actually more energy hungry than others? For example, if I increase more SRAM, or if I increase something else, like what's the energy curve?
Yeah, actually, we didn't test that part. It can be executed in the future work. As we do not know how the impact from the outside, like the CPU and the SRAM, DRAM, but I think the impact is less compared to the I/O request and the inner resources inside the SSD.
Yeah, I mean, I was like more interested in inner resources only. So when someone sells a PCI SSD or a SATA SSD, so they have internal resources apart from normal SSD channel and SSD bank. So for example, SRAM and they have ARM CPU and like that. So did you like, for instance, if I increase the CPU frequency, which are embedded in SSD disk, so what are the effects there?
It's hard to say, but maybe we can talk about this later because maybe I need to refer to our former works to get the results. Okay. Thanks a lot.
Yeah. Peter Desnoyers, Northeastern. Was interested in looking at one aspect of this, which is basically for a SATA drive, you have one power budget. For a PCIe drive, you have a much larger power budget. Yeah. To what extent is this just people will spend what you give them? You know, if there's no penalty to spending more power, then, you know, if you get any advantage from another channel, you'll add it to make your device faster than the next guy's.
Yeah. So in these papers, we want to mention that the power effect and the energy effect has already impacted the performance. So what this purpose of the paper is to let other researchers know we need to make optimizations about the power and the energy so that the performance can be impacted very less.
Okay, so even though it's within the strict budget, it's already too high.
Yeah.
Thank you.
Thanks a lot.
Xiao from QCRI. I'm curious, in your conclusion, you mentioned that those power or energy consumption higher than traditional is not acceptable in today's workplaces.
Yeah.
So apparently there is this trade-off between performance, their higher performance and their higher energy consumption. Yeah. By executing faster, they also save the CPU and memory, all those components, energy. So how do you take that into the picture?
Excuse me. Could you repeat that again? What's the meaning of CPU and SRAM?
Because when the SSDs are faster, they allow the request or the whole computing task to finish in shorter time. Yeah. And it seems that the CPU side, the host side, burns more energy than storage anyway. Yeah. So have you taken that into account?
No, we didn't take that into account. We just talk about the power and energy issues in the SSD.
So I was wondering, when you did these tests, you drove the SSD as fast as you could, right?
Yeah.
So did you look at all into the recovery time? So if you drive the SSD for a while and then you stop, how long does it take to cool? Because many workloads don't drive the SSD at 100%. They're intermittent, so maybe the SSD could actually stay below this throttling temperature of 180 degrees?
Oh, this is very good questions. I think we can make it. We can make it in the future, and to test this how it works. Thanks a lot.
Okay. All right. Well, I guess we're done a little bit early. So thank you.
Thank you.